And I thank the organizing committee for the invitation and then for having the opportunity to work about one of our actual research field, and that is the sulfur combustion as closing step in a sulfur-based solar thermal cycle. So first of all, sulfur and industry, then the use of sulfur in a solar thermal cycle, the project itself, which acronym is Pegasus, its concept, partners and facilities, and the sulfur combustion itself, which is investigated at KIT in Karlsruhe. So this slide reports the sulfur world production in 2014, and it's about 70 million tons. Most of it, as we can see, comes from the refineries as a byproduct. A significant part is produced by the metallurgy industry, then for mining and from different sources. Some rough numbers, just for fun. 70 million tons would produce 180 million megawatt hour, knowing that in Germany, 1 kilowatt hour electric is 30 cents versus 15 cents for fuel. Sulfur is also available on the Earth. In the continental crust, there is 350 sulfur versus 200 carbon. So sulfur is used mainly for the production of sulfuric acid, which is so important that it is a measure for the industrial strength of a country. Until now, that may change. 60% of the sulfuric acid production goes in the fertilizer production. The rest is used for pharmaceutical, detergent, paint, catalyst, and so on. So sulfur comes from desulfurization of hydrocarbons via Claus process, and also in a non-negligible part from ore roasting. So before continuing, it means that actually sulfur, it's a waste, can we see? It's a byproduct. Sulfur then is cheap. Sulfur is transportable. Sulfur is easy to handle in a liquid or in solid form. In the liquid form, is the molten sulfur can be transported by train, pipelines, or trucks. However, the containers have to be heated up to 150 degrees Celsius. The solid form is in granulate and is also easily transportable, as we can see. Now, if we compare, as what we see in the morning, if we compare now the energy storage density among hydrogen, gasoline, sulfur, and lithium battery, molten salt is actually used only for thermal storage. So we see that sulfur is not that bad. It's about 10,000, almost comparable to gasoline, but far away from lithium battery. And the volumetric energy density in kilojoule per liter, we see here that we have half of the gasoline, far away from the lithium-ion battery, and the hydrogen is 6,700, but it is at 700 bar. So, as I said, it's available, it's cheap, it's transportable, it's cheap, and it's available everywhere in the world. In North Germany, sulfur is formed in Bracke from the purification of natural gas. And they have all the facilities to handle liquid sulfur and also solid sulfur. They even have devices to fill directly the ships. So, based on economical and practical factor, a project based on sulfur has been developed And the aim, the goal is then to a development and demonstration of a solar tower system using solid particles. And these solid particles are combined with thermochemical solar energy storage, and all that is based on elemental sulfur. The goal is to obtain dispatchable, renewable electricity generation at low cost. For that, the solar tower in Jülich is already available to do on-sun concentrated solar irradiation. The partner, we are 6. DLR in Germany, which owns the solar tower. They are also responsible for constructing the reactor. I will talk about that later. APTL in Greece is the developer, or has to develop a suitable catalyst for the decomposition of SO3. In KIT, in Karlsruhe, we will do the combustion of sulfur itself. Batic Ceramic in Poland, sorry, I forgot that. In Batic Ceramic, they work together with APTL, and they manufacture the particle, the ceramic particle in which there is the catalyst. So they have to work very close with the APTL. Then we have Processi Innovativi in Italy. These are power plant designers, and they help, under others, in the design of the sulfur with input data. Bright Source in Israel is a concentrated solar plant designer, and their role is to transfer to help in the transfer of the operating power solar plant to a large commercial scale. So, what is the actual technology? We have a refinery. We have production of sulfur. Sulfur is sent to a sulfuric acid plant to produce sulfuric acid. And actually, some electrical power is also produced from that. What we want is now to integrate some particles, solar particle, by using solar plant. What happens here? The mirrors or heliostat catch the sun and warm up the particles. The particles are used to split the sulfuric acid into SO2, then through the disproportionate reactor to sulfur. And sulfur is then sent in the sulfur gas turbine plant to produce electricity. So if we want to integrate the yellow arrows in the existing facilities, we need a refinery. But if we want to do separately, we can even remove the refinery as long as we have enough sulfur stored. To store sulfur is easy. So, what are the objectives of Pegasus? We need to develop ceramic particle for SO2 splitting, and with the oxide catalyst. We need, that is not sure if it will be done, we need high temperature particle storage system at 900 degrees C. Here we need a cascade for the decomposition, the evaporation and decomposition of SO3. Then transfer the technology to laboratory to on-sun condition and under real solar irradiation. And in Karlsruhe, we will develop and construct a lab-scale sulfur burner able to modulate in the range of 10 to 50 kilowatt. And we want to obtain 5 megawatt gas turbine application, high efficiency combustion, and a power density of 1.5 megawatt per cubic meter, and flames above 1,400 degrees Celsius. So now we can look in details. Let's start here with sulfuric acid. Sulfuric acid is sent in the evaporator. Then we have SO3, which will decompose to SO2 and O2. At the exit here, we do some gas separation, and we follow SO2 through disproponate reactor to produce sulfur. And sulfur is sent to the burner. And the combustion of sulfur generates high quality heat above 1,200 degrees Celsius excess, suitable for electricity generation using a gas turbine. Let's come back here. We need some heat, a lot of heat, to do the evaporation and the decomposition. This heat is given by solar field. The sun is tracked by the mirrors and are sent in the receiver, in which the particles are warmed up to 900 degrees C, and by falling, they give the energy necessary to evaporate and decompose sulfuric acid. And at the bottom is cold again, and they will send back up. There is some heat recovery, but unfortunately, at this point, it's too complicated to reuse it. Now, if I split the diagram in two parts, we have on the top the solar part, and on the bottom the non-solar part. What does it mean? It means that this part is actually not dependent on the sun. So if it's raining, clouds are passing through, only the decomposition of the sulfuric acid will stop. Here, the electricity can continue to work around the clock as long as sulfur here is available. And as I said before, sulfur is cheap, sulfur is easy to handle, sulfur is transportable, and we can store it. Now, some energies. Here we need more than 800 kilojoule per mole, but we recover here some energies as well. In the black point, there is some energy exothermic reactions as well, but these two are not usable. And the efficiencies, it has been calculated that the efficiency here is 60%. The rest is lost, for example, because the mirror, there is a bad adjustment of the mirrors, or there is a lot of dirt, or there are so many problems. And the 90% here have been measured. So roughly, or in general, we can say that the whole process has an efficiency of 21%. So as far as I know, I may be wrong, the production of hydrogen efficiency is 13%, so we are a little bit better, if I'm not wrong. So now we want to transfer to the on-sun condition. For that, there is a solar tower in Jülich, which is unique in Germany. So we see here all the mirrors, each mirror is movable, adjustable. The sun is tracked and sent in the tower here. The tower is 60-meter height, in 8 hectares, and there are about 2,200 movable mirrors with a surface area, with a very large surface area. So maybe I come back. So the receiver here is somewhere here. And the basic concept is that we need an inclination angle, and the particles are from the top, they are cold, and they come down, they are heated. And we can see better here. Here is the receiver, not this one. This one is used for something else. This is the receiver. We see here the receiver operating. We see the sun. the reflection, and inside is what we see, cold particle, and at the bottom warm. And the temperature inside, the reach temperature is 900, and that has been tested many times through the CenterRec project, which is finalized now. So, now, what do we have to do in Karlsruhe? We have to develop a sulfur combustion at high power density. We have to develop some chemical kinetic mechanism. For example, to look at the flame velocity, we do some CFD simulation to support the development of the burner before, and then the design of an atomization and combustion. We need an atomizer to first to do the combustion and to go ahead with the experiment. So after concept, the burner conception had the following specification. We use air in an air compression ratio of 15 and 720, and what we reach is 20 kilowatt at laboratory scale at 1 bar, and 5 megawatt you at 15 bars by using 16 burner. The turbine will work in the range of 1500 K to 1700. These input data have been calculated by Processi Innovativi, and the air-sulfur ratio has to be 7.2 at about 1800 K. But it could be better if we could reach a ratio of 10 at lower temperature. But that could be a problem because the flame can extinguish. So we will check it with the experiment. So before burning the sulfur is liquid. So we need first to spray it. It will be sprayed first, and then it burns. So we need atomizer. And we have looked at 4 types of atomizer. And the main characteristic is the Southern mean diameter, which is based on many empirical reactions based on Weber, Ohnesorger, Reynolds numbers. But we can just see that SMD is defined as the diameter of a drop having the same volume to surface area ratio as the entire spray. And it has to be as small as possible. So among these 4, we have 4 atomizer, and here we have the conditions at 15 bars and 1 bar. That's what we want to, these are our preliminary conditions. And as we can see, at 1 bar, it seems that the pressure swirl nozzle has the best, it shows the best performance. And at 15 bars, it is the pre-filming air blast atomizer. We are going to construct both of them. So now we have the atomizers. Now we need to look at the shape of the flame. And that is based on these 2 types, the attached flame and the lifted flame. On both sides, there are positive and negative points. This flame, the attached one, is an inner recirculation zone, while the other one is outside. The flame is more compact, which is good, but there are a lot of risk that the droplets stick on the wall. On the other side, here we have, through that it is lifted, we have an increased premixing, which is better, and more time for evaporation, and then we have less NOx emission. So here are some CFD calculations which have been done. for non-reactive spray without combustion and with the combustion itself. Actually, the combustor, the nozzle is already constructed, and it looks like that. And we see that inside we have the pre-filming and the pressure atomizer. Both atomizers are incorporated into the nozzle, into the burner. We can switch from one to the other one. And here is, so here we have the evolution of the injected particle, so it's only the spray with attached flame. And of course, these are the droplets, but they're not that big. There is a factor of 40. Here is the flow rate, and we see the calculations show how the broadness of the flame. We see also there is some recirculation in the middle and outside. On the other side, the theoretical temperature, because there is no combustion, we see that it's colder outside, meaning that the particles are getting warm and starting to ignite. The flow velocity and temperature shown here are with combustion. Of course, it takes a long time to do those calculations. People know that. People are doing CFD calculation. So the CFD attached flame, the flow velocity, and the lifted flame. We see here a recirculation zone, and actually the reacting zone is here in the middle. We don't see it on the flow velocity, unfortunately. On the other side, the particles are going up, and the reaction zone is exactly in the middle, and it's vertical. The temperature is showing that in the middle it's warm, and outside a little bit cold. And here also that in the middle it's warmer. So that needs also to be validated. So here are the parts which are already constructed. And what we see here is inside. Everything is inside, we cannot see it. And this is to swirl, to generate the swirl, and that is for the pre-filmer. So it will look like that. We have a sulfur melter. Sulfur is liquid, and we'll send in this container. From the top, we will send nitrogen to increase the pressure up to 200 bar at 420. Then the whole thing is sent in the atomizer or combustor. Here we can do either atomizer alone or both with combustion. And then before SO2 is produced, which is harmful, it has to be neutralized, and it's sent in a treatment unit in which it will be neutralized with a basic solution. The setup, the final setup would look like that. So this is actually the original, the size of the final setup. So now, our task is to develop the combustor and to manufacture it, but it's also to develop kinetics. Kinetics, we need it to put it in the CFD simulation. The CFD simulation helps for the design of these two parts. So very rapidly, what do we need? First, literature research on sulfur. Then use what has been, see which method have been used for sulfur, and do some validation of the method. Of course, the higher the method, the better the results, the accuracy, but with sulfur it's not that easy, so we have to find a balance between accuracy and computational capacities. The calculations are based on electronic structure theory, and we obtain energy geometries and etc. using Gaussian. With that, we can calculate thermochemistry. We we can think that there is enough thermochemistry in the literature. That's right. There is a lot with sulfur, but it's always combined with something else, and mainly with carbons and also with hydrogen. Molecules like that are not easy to find. Or if we add nitrogen, because we are working with air, so that's it blue in nitrogen, that also is not easy to find in the literature. So after that, we can then do some kinetics and then do some simulation. So the first thing then is to find the method. We have taken values, molecules, which are well known, SO, SO3, SO2, and SSO. The enthalpy of formation is well established in the literature. Here are the literature values, and we used different basis set. And surprisingly, none of them is in agreement with the literature. The geometries calculated by the FT is in perfect agreement with literature. The problem is with the energy, so we have to be careful with that. So we switched then to ab initio method, to composite method, CBSQ, and the other one. W1U is one of the most accurate, but it needs a huge capacity it needs a lot of calculation capacity. So it is used only when the molecule is small. So, and the comparison here is very good, as we can see it. The spin number is of crucial importance. It has an enormous impact of the calculation of the energy and therefore on the kinetic and thermodynamic. Another test is calculating the SO bond from the dissociation of SO3 to SO2 plus O. Literature is saying that it's 83 kK. On the left, DFT, on the right, ab initio, and we see here the poor results obtained for the bond energy, while here we have a variation of 3 kK. The bond energy for SO2 to SO plus O is 130, and here also is not good, while here it's, I can say, very good. So we did some thermodynamics, some kinetic calculation, and some reaction as example, and also some nitrogen reactions. These are only examples. We are far away from the work. So if we take two molecules of SO2, we see the attack of the oxygen on the sulfur, forming a relatively stable molecule, which can dissociate to SO3 and SO. What is if we have two molecules of SO3? We see here the same kind of transition state, the oxygen attacking the sulfur, and we obtain a relatively large molecule. This molecule, for example, is not calculable with the W1U method. It needs too much capacities. So we can now dissociate it, or dissociate to SO2 and SO4, and SO4 itself can dissociate to SO2 and O2, and we can go on like that. Now, if we take the calculate S2 plus O2, we have a sort of peroxide, but I have to point out that for these combination, for this association, there are many reactions, there are many possibilities and many products. So that is only one example. The peroxide undergoes an intramolecular abstraction. So the oxygen moves to the sulfur and forms a stable molecule, as we can see here. And this one can dissociate. It's quite high, but it may dissociate to form SO2 and S. If we now introduce the nitrogen, because as I said, we are working with air, And we have here an example of S2 plus NO. We obtained a very nice transition state where we see a very nice addition to form stable molecules. But the terminal sulfur will move and go to the oxygen to form another isomer, which itself dissociate to SO and SN. And here, the barrier is relatively low. Addition of SN plus O2 now gives also a peroxide. That is also only one possibility. There are also another, we can add it in the transposition, and we have another product. But if we add that, we have a peroxide, and the peroxide also undergoes an intramolecular abstraction. So the oxygen goes on the sulfur. Why? Because it's a lot more stable in this form. The continuation is then a dissociation here to SO and NO again. So before going ahead and trying to put reactions together, we wanted first to look at the literature. What is the literature saying? So there are a lot of reactions, but only 11 reactions, as far as I know, but we've looked a long time, only 11 reactions are involving S and O. All others have carbons of sulfur or other things. So with these reactions, we did a simulation using Chemkin, but also we used Cantera to check. And we did the calculation at 1 and 5 atmosphere and 2 temperature, and we looked at the burning velocity. And that is the burning velocity, which looks usual. We have here centimeter per second as a function of the air-fuel ratio. So under 1, the flame is rich, and above it's lean. So the profile, this is a typical profile, which increases when the temperature increases. What is unusual, it's the value of the flame velocity, which is 300 centimeters per second, which is extremely high. And at higher temperature, it's even higher. So we just did a sensitivity analysis and to see which reaction has the most impact on the system. So everybody knows that, but the longer the bar, the more important is the reaction. And it seems that reaction number 1, this one, has the most important impact on the system. We looked at the literature again, so there are 3 different reaction rates, and I hope he will not have, he's here, I know. So we have 3 different factors, and with that we have calculated to compare again, so we are again here 300, and with the diesel value it's even higher. So what we did is reevaluate this reaction. We started with S plus O2, forming SOO, and SOO dissociate to SO plus O. We have a singlet and a triplet calculation because both of them are existing. And the new calculated velocity is at 373. It's around 78 centimeter per second, and here around 93 centimeter per second, which is actually more realistic. I'm not saying that we are not pretending that is right, that is the right numbers. If we compare, we see that we are here, and that is the literature. But as I say, we don't know what is right. We hope that the experimental part will tell us where is the right velocity, because it's extremely important here. So we have here a number of dancing molecules. These are all transition states that I hope that we will have reactions if it works. Sometimes it's not realistic, or the results are completely absurd. So I hope that we will have it. And the conclusion is for the whole project is that sulfur has high thermochemical energy density. We have efficient transportation and storage or solid and liquid sulfur. Solar sulfur cycle allows for baseload power production. There is a potential for integration of sulfur cycle into existing sulfuric acid plant. And concerning the project itself, we have development on sun testing of catalytic active soil particles. Construction of particle reactor for sulfuric acid splitting is also done. Prototype development of sulfuric burner for gas turbine are also done. And we did some simulation. And what we have to do more on in KIT, we have to continue in the development, because we still didn't start the combustion itself. So there is also a few things to adjust before starting the combustion. So some kinetics has been done, and a lot of kinetic has been done, still done. We use some CFD result to put in the CFD model. And in the laboratory, so the setup is actually finished, it's done. And it has been done with the help of CFD simulation. So, and some experiments have been tested on atomizing, and they look quite promising. So, if you want to read more, there is a website on Pegasus. And thank you. And I see that I was faster, and it's okay. Okay, so thank you.